A binary search tree is one of the most powerful data structures in computer science. And once you see how it works visually, it becomes obvious why. Every single node in a binary search tree follows one simple rule. Values smaller than the current node go to the left. Values larger go to the right. That one rule applied consistently at every single node creates something extraordinary. A structure that can find any value in O log n time without searching every element. Watch as we insert values one by one. The first value becomes the root, the top of the tree. Every value after that travels down from the root following the same rule at every node it passes. Is the new value smaller than this node? Go left. Is it larger? Go right. Keep going until you find an empty spot. That is where it belongs, permanently. Notice what happens to the shape of the tree as more values are inserted. Left subtree holds all values smaller than the root. Right subtree holds all values larger. And within each subtree, the exact same rule applies recursively. Now watch how search works. We are looking for a specific value. Starting at the root, is our target smaller or larger? We eliminate half the tree instantly with one comparison. Move to the correct child. Ask the same question again. Eliminate half of what remains. Keep going until the value is found, or we hit a null node, meaning the value does not exist. This is why binary search trees are so powerful. Every comparison eliminates an entire subtree. With a balanced tree, that means O log n time for search, insert, and delete operations. The critical word is balanced. If values are inserted in sorted order, the tree degrades into a straight line, losing all its advantages and becoming O n time. That is why self-balancing trees like Avel and red-black trees exist, left for smaller, right for larger. Recurse. Subscribe for more algorithm visualizations every week.